Welcome to this presentation on data-driven TLP tendon loads from internal hole fiber optic sensors. My name is John Hedengren and I'm a professor at Brigham Young University. We appreciate the invitation to be able to submit this presentation and paper at ASME OMAE 2023. And my colleague Zachary Hillman is giving the presentation there in Melbourne. A little bit about Astro technology. We have advanced instrumentation for subsea fields, pipelines, and risers, topside offshore oil platforms, and also space instrumentation. So the company actually started in rockets and be able to monitor for the demilitarization of ICBMs and be able to instrument those with fiber optic sensors, but also involved in things like the Robonaut hand, and the offices are in Houston. So engineering capabilities of this company are system integration, real-time embedded systems, experimental stress analysis, fiber optic sensor technology, conventional sensor integration, and then also environmentally hardened systems and software development. So here are some of the previous applications, instrumentations on risers and flow lines. And you can see the strikes here, and then you can see a sensor station that was applied. Actually, it's right down here is a sensor station where the fiber optic sensors were used to monitor these risers and be able to monitor things like vortex-induced vibration. You can see also here some clamshells that are put on during the pipe lay procedure to not damage the fiber optic installation and the sensor clamps that are placed on it. So you can see a few of those that are right here. And then you can see also a fiber optic cable as it descends here. Okay, so there's better need for instrumentation. We want to be able to detect early warning signs of fatigue or failure. Also in flow lines, be able to detect things like plugging, fouling, and be able to monitor flow lines in real time. And also be able to automate the monitoring of these critical systems. We want to be able to track pressure, temperature, strain, and flow, and do all of that with these non-electrical fiber optic sensors. Also be able to give critical data for key decision makers, whether that's a program that automatically monitors and takes action, or to operators who are monitoring wells or flow lines, risers, tendon tensions, and so forth. We want to be able to eliminate production downtime and be able to take a proactive and telefield approach where we're sensing real time this infrastructure that is deep water below the surface and it's difficult to be able to reach. And so we want to be able to measure that, develop a type of nervous system for this infrastructure to be able to sense real time when there's a problem. Also be able to prevent asset damage and pipeline leaks and reduce safety and environmental risks. So we want to talk about this specific application that we've developed with this tension leg platform. And this is in the Gulf of Mexico on the Neptune Platform that was owned by BHP, but now by Envin and then Talios now. There's load cells that monitor the tendon tension, and these are built into the original design of the TLP platform. The load cells, however, are failing just due to water ingress and other issues with the aging of these load cells to be able to estimate or measure tendon tension. So the approach was novel. This was to monitor the tendon tensions, not sending divers or ROVs into the water, but to install these sensors on the internal of the hole. Be able to do a dry install on the webframe of the pontoons of this platform and determine if we can estimate the tendon tensions. So I'll talk a little bit about the system environment, a little bit about the preparation that we made to be able to prepare the web frames for this installation, a little bit more about the installation itself, some sensor selection, and then model training and performance. So let's first of all talk about the system environment. So here is a photograph of the Neptune platform platform. It is has these 3 pontoons, and it's a tendon leg platform. So there are tendons, okay, 2 at each of these that then descend down to the seafloor and attach, and be able to maintain the tendon tensions is critical. So somewhere between 3,700 to 3,900 kips, in that range for each of these tendon tensions. And we want to be able to route these signals back up to the control room for the operator to be able to monitor the tendon tensions. So here's just an overview of the TLP design. Here you can see the tip tank. Okay, so over here is right at the very end. And you can see the walkway here. You can see these web frames that come down. And that provides a stiffness for these pontoons to be able to support the stresses that are induced by the platform. Okay, so some of the preparation. We had to, first of all, do the cable integrity and make sure that we had the, as we pass through these bulkheads, that we maintain watertight integrity. And then we also did an FEA sensor placement, so finite element analysis, to determine where was the most sensitive place on the web frames to be able to install these sensors. And then about the data management as well. We had about 1 terabyte of data coming in each year. So how do we use that data to both calibrate and monitor the system in real time? So first of all, the ruggedized, the fiber optic cabling. This is the cutaway of the fiber optic cable as it goes through the bulkhead. So all of this is the armored cable with the fiber optic sensor that comes through the center, with a polymer jacket and this ruggedization to be able to allow just the signal to come through right here through the center. Okay, and then now let's talk about where we placed the sensors. So we did a finite element analysis thanks to Wolfstar. They provided the service to be able to detect, as the tendon tensions change in simulation, where are the stresses that are induced in this web frame. And so you can see a little bit of the meshing that they used for this simulation and determined the sensor location. So you could see a block of sensors and then some up here as well. And this is specifically where they were placed with the wavelength that we put in there. So this was a 1480 to 1620 nanometer swept laser fiber optic interrogator that we used, that was sampling at 5,000 hertz to be able to detect the signals. We had to downsample. It was downsampled an average down to about 10 hertz because that's all that the operator really needed, and then they were looking at 20-minute averages on top of that. So real-time data collection and analysis with these sensor placements. Now, we used a couple different web frames. This one was in the tip tank, but then we also had one that was a little further back in the web frame, in the dry part of the web frame. So this was the wet bulkhead, and during normal operations, the ballast water is placed in there to be able to balance and maintain the tension on the tendons. And so we had some installed in this area, but also in a dry bulkhead further back in the pontoon. So this was a little bit more about the data sampled at. We had one fiber optic interrogator that sampled at 5,000 hertz and then 1,000 hertz. So we used the one that had the 5,000 hertz in the end. So we want to save just at 10 hertz, so downsampled from that, and then transferred the data by Modbus to the control system. And we could have used OPC-UA or some of the more modern standards, but the existing platform needed Modbus for this. So a little bit about the installation. We had some surface preparation that we did in the initial part of it, and we learned a lot from an initial installation and then came back and did a subsequent installation with additional sensors. One of the things that was critical about this was the relative humidity control during the installation, to be able to have a dry environment, especially in that tip tank where there's ballast water that was just recently removed. And so it's a very damp environment. Be able to control that humidity, and some of the methods that we use were really critical. Also, adhesive selection and passivation of any corrosion was also very important in this project. So here you can see the surface preparation. Some of the remaining ballast water was placed here in some of these bags just to be able to pump out those last few inches of water. You can see that the surface was ground down to bare metal here to remove some of the coatings there. And then this was for the cable routing. And then this would be another sensor station here that they are preparing. All right, so here's some of the fiber optic installation, some of the with bare fibers, and then also with some ruggedized fibers. So we tried both methods and found good performance with both of them. Okay, so here's the finished part of it. In the wet bulkhead, there's going to be sloshing here with a partially filled in this area, and with the platform tilting due to wave action and currents, then there's a wave action also inside of this wet tip tank. And so we had to ruggedize this. Here you can see the sensor installation, and then here the cable routing, just adhesive to this web frame so that the fiber optic cable does not move. Okay, so sensor selection. Now I mentioned the first installation that we did, internal hole 1 sensors, and this is pontoon 1, and we placed 12 in the in the dry, and then 14 in the wet, in the R web frame versus the K web frame. And there you can see the different pontoons and the counts on those. Now this one we did fewer sensors. We just ran out of time for the project. We could go back and install additional ones, but we actually found that we were able to get acceptable performance just from the 36 sensors that were placed on that one. All right, so we need to also take a look at temperature compensation. This is a really critical thing with fiber optic sensors, be able to calibrate and remove the effect of temperature. And so we had some specific temperature sensors that were placed at strategic locations below and above the water line for the ballast water, to be able to detect the differences in temperature and be able to monitor that throughout the year. So here you can see 2021 from July all the way to 2022 to November. And you can see an annual cycle of the temperature during the winter month versus the summer months. So we had all of these sensors. They agreed fairly well in terms of the overall seasonal variation of the temperature. And you can also see sometimes where it doesn't follow that sinusoidal expected value due to things like loop currents or other things that bring warmer or colder water into the Gulf of Mexico. All right, then we had so many sensors that we wanted to rank their importance. We had done this finite element analysis to determine what we thought were going to be the most important sensors. But then we could also, once we had the data, be able to use a type of selecting the best sensors with a chi-squared statistic to tell us how the features, the inputs to our model, related to the outputs, or things that we were trying to predict, which were the tendon tensions. And you could see certain sensors ranked higher than others, and some of them were much lower. So we use this feature importance to be able to eliminate some of the sensors, because any one of these sensors that goes bad, then it could affect the entire correlation. So we wanted to reduce the dependence on just many sensors on the platform. Okay, so now model calibration and performance. We had about 1 terabyte of data per year that we were collecting with this. We wanted to make sure that we could calibrate to the existing load cell sensors. And one of the things that we saw is some methods for linear regression perform better than others in terms of scale up. As you have number of data samples that goes up to 1 million or tens of millions or 100 million data samples, this is the amount of time to train those. And with different packages that are listed here in Python, you'll notice some of the packages like Keras, TensorFlow, if you use those nonlinear packages, they do not scale as well, but you can parallelize them and potentially be able to spread them out over many GPUs, especially if you have a neural network or other type of nonlinear regression that you want to do. So those are the PyTorch, Keras, TensorFlow models. As you can see, all are in this region right here. Then you get down to the linear regression methods, and you can see the SciPy linear regress was the fastest. Now OLS, stats model OLS, that gives you more summary statistics. It really helps you calculate some of the things like p-values or other things related to the regression. So we also liked using that one, even though it was a little bit slower. In the end, we did use linear regression to relate the strain peak values to the tendon tensions. And here are some of the results. Here you can see the training period. These are some ballast movements. And then this is normal operation. And then you can see a validation period a couple months later where we took some of the data and we've increased that amount of validation data even more as we've collected that. But just for the purposes of the publication, these are the results that we had at time of publication. But excellent results in terms of fitting to the model and long-term stability of these sensors. Let's look at not at the yearly view, but just at 60 seconds. And here you can see how it's tracking with the existing load cells versus the internal hole sensors. You see excellent agreement from all 6 of these tendons in terms of the tracking from the internal hole to the load cells themselves. Then you can also see tide cycles. So this is over multiple days, where this is a typical tide cycle. One of the reasons why you see this variation here, this is just due to wave action. And then the longer one, that is due to the tide action. So excellent agreement even with the changes in the tide, where the water level comes up and down and it affects the tendon tension by, in this case, by about plus or minus 50 kips. All right, so key takeaways from this is that we have some internal measurements that relate to external conditions. We're able to measure something in a dry bulkhead of this pontoon to be able to estimate the tendon tensions without sending divers or ROVs into the water, to be able to install the sensors directly on the tendons. Now there's high sensitivity. We saw that with the wave action and then also with the tide cycles, and then also over a longer period of time, over a year, with training and validation. There's a low error. We needed plus or minus about 1% error to be able to satisfy the requirements of the monitoring of tendon tensions. It's also able to withstand disturbances, especially because we had so many sensors installed. We have a lot of redundancy. We had to down select some of the sensors, be able to just use a subset of those, and that was sufficient to be able to maintain the accuracy. Potential future applications. We want to be able to mitigate vortex-induced vibrations, or VIV. There's service life extension applications as well for risers, where we can monitor but also repair some of the fatigue in the riser. Also, mitigation of subsea anomalies before they occur. So, for example, flow assurance. We've done other flow assurance applications, extreme load on jumpers, and fatigue monitoring and mitigation. So appreciate your attention for this presentation, and we're happy to answer any questions during the OMAE meeting or afterwards if you'd like to reach out with more questions about the technology and how it might be applied for subsea or other types of monitoring applications with vessels, ships, subsea, deep water, flow lines, risers, and other types of mooring lines or other infrastructure. So please reach out. We'd be glad to have a discussion. Thank you.